In this video, we will start discussing the continuity of a function. So what is the continuity of a function? We say that the function f of x is continuous at a point, let's say a, okay? If the limit of f of x as x tends to a exists and equals f of a, okay? So this is the definition of continuity that we are going to be working with. Now, notice here, this definition requires first thing that the value that f can take the value x equals a, okay? Better, that a is a valid input for f, or a is in the domain of f. It also requires that the limit as x tends to a exists. Okay, that's the second condition here. And the third is that both these quantities, the limit and f of a, both must be the same, okay? All right. There are alternative ways that we can think about continuity. So we can think about it as thinking that the small changes in x produce a small change in f of x. Okay, if you wish, a function is continuous if small changes in the input produce small changes in the output. Okay, there is a small error in the input, then there will be a small error in the output. Another way we can think about it is more graphical, if you want, is if we can sketch the graph of f without lifting the pen. Okay, so these are the three ways we will be thinking about continuity. Okay, so we may think, well, aren't all functions continuous? No. There are three main types of discontinuities. Okay, so let's see examples first of things that can go wrong. So discontinuities, they can be of three types: a jump discontinuity, an infinite discontinuity, or a removable discontinuity. Okay. So let's see, a jump discontinuity. Here the function is not continuous because there is a jump in the values. Okay, so for example, we could have a function f that goes all nice and smooth up to a certain value. Okay, but then suddenly it jumps and it continues whatever. Okay, something like this. Okay, so this is our f of x, and we can see that here the value of the function suddenly jumps. Okay, appears somewhere else and continues. Okay, so this one is a jump discontinuity. Here the limit as x tends to a of f of x does not exist. Okay. Now the second possibility is that it's an infinite discontinuity. Okay, what happens if it's an infinite discontinuity? In that case, we have something of these vertical asymptotes. Okay, the ones that look like a chimney. So here at the point A, these points writing are the point A in the definition, okay? In this case, the limit as x tends to a of f of x is infinity or minus infinity. Okay, so you see that here it kind of jumps, okay, from one side to the other of x equals a. Okay, another third possibility is that it's a removable discontinuity. Okay, this happens. This type of discontinuities, they feel like the only problem they have is that there is a problem of definition. Okay, somebody didn't define the function properly somehow, if you want. Okay, here, there we go. What happens is that there is a misplaced point in the graph. Okay, that we follow, and suddenly there is a gap. In that gap, the function is defined as something else, and then it continues as if nothing happened. Okay. In this case, what happens is that f of a exists, but it's different from the limit as x tends to a of f of x. F of x also exists. The limit of f of x also exists. Okay. Now, these are examples of things that can go wrong. What are examples of things, of functions that are continuous? So every standard function is continuous. Okay, so standard functions are continuous. Okay, these are continuous everywhere in the domain, okay? So these are continuous wherever they are defined. Wherever they are well defined. Okay. So for example, 1 over x, well, I don't know, the logarithm, the natural logarithm, the sine of x, the exponential of x, polynomials, x squared, and so on. So many. Okay, the ones we are used to. So for example, if I pick 1 over x, this one is continuous when x is different from 0. The logarithm, whenever x is positive, okay? And then the sine of x, the exponential, and x squared continues everywhere. Okay, we just need to find the domains, and that's it. Okay, more good news about continuity. So what can we do? Once we know that these functions are continuous, then that's good news because continuity respects operations. Okay, respects addition, subtraction, whoops, multiplication, division. Okay, here there is a problem. The division is okay as long as the function we are dividing by doesn't become 0. Okay, so here, exception, except if the denominator is 0 or goes to 0. Okay. Oh, and then there is well, there's another very important one, that is that continuity respects composition. Okay, so we have addition, subtraction, multiplication, division, and composition. Okay, here we need to also, how would we write this down? Would be limit of f of g of x equals f of the limit of g of x as x tends to a, okay? For this to be true, we need f to be continuous. Continuous where? At g of a, okay? And we also need g continuous at x equals a. Okay, if these two work, then there is no problem, okay? This is easier when we see it in an actual example. So let's work on an example to consolidate this idea. But you see that basically we are dealing with all the concepts we have already seen in previous videos. We need the domain of a function, right, to see where the function can be continuous. Okay, and we are also dealing with the composition here that we were discussing. So let's say, for example, that I give you this function, the limit as x tends to 1 of the sine of x squared minus 1 divided by x squared, x minus 1, okay? And now it would be a great time if you want to pause the video, try it by yourself, and then we can compare notes, okay? So let me go ahead. By this property we just said, we have clearly two functions here, right? The sine and then whatever is inside. So we can use, because they look fine, they are continuous, except at x equal 1 maybe because of the denominator, right? We can just bring the limit inside, okay? The sign is continuous, so this is sine of the limit as x tends to 1 of x squared minus 1 divided by x minus 1. Okay, and here we will write sine is, sorry about that, sine is continuous. Okay, it's continuous everywhere. And then when we look at this, this limit here, the limit as x tends to 1 of x squared minus 1 divided by x minus 1, we did this in the previous videos. Okay, this is like 0 divided by 0, but that is if we don't look at it properly, okay? Because if you notice, let me just go ahead, get rid of this. I have x plus 1 times x minus 1 on the numerator divided by x minus 1. So what is this limit? Is 2. So then the limit of this whole expression here, right? It's going to be the sine of 2. Okay, so you see the way we did, we brought the limit inside the sine function because the function is continuous. Let me do one more example. So let's say the limit as x tends to 2. Let's do also 1 of the natural logarithm of x squared plus 1. Okay. So here the logarithm is continuous. Not everywhere, but is continuous for all positive numbers. And we have x squared plus 1 that is strictly positive. It's bigger than 0, right? Because it's a 1 that is bigger than 0, and we are adding x squared. So no matter what x you pick, it's always 1 or bigger. Okay, so yeah. So by continuity, we can just pull the limit in the logarithm, and we have, so the limit of x tends to 1 of x squared plus 1. The limit respects the sum, right? We know this, so this is 2. So it's the logarithm of 2. Okay, and those are the results, sine of 2 and logarithm of 2.